Anyway, so I really would like to enjoy, I mean, I would like, yeah, to enjoy myself because I like these problems, so to share these problems with you. Probably some of them are known, to most of you, but nevertheless, I will try to give a kind of, history and embed these problems in a kind of general context. I've been working on exterior domains for a while, and was one of my main topics, interesting topics that I have been working on over the last 50 years. Not the only one, but one of the main. And so after almost half a century of work, I picked out these three problems that, in my opinion, are really amazing. I mean, interesting, but it's also a question of taste. So to me, they're really very interesting, and probably they're even more interesting because they're unsolved. So, as I said, I would like to share these problems with you. Okay, the whole thing is three-dimensional, okay? Because if I start talking about the open problems in the two-dimensional case, it would take 1 week. So everything is three-dimensional. All right, so the scenario is that we have a rigid body that moves with, is translating and rotating in a viscous fluid that fills the whole space outside the body. The viscous liquid, of course, is Navier-Stokes. Nu is the kinematic viscosity, and omega is the region that is outside B. So, okay. So now we have two cases. I will distinguish two cases. Case A, where the motion of the body is prescribed. So I say that B is passive. And the case B, when one of them or both are unknowns. In that case, B is active. So the motion of B is part of the unknowns. Okay, so it is convenient to describe the motion of this body from a frame that is attached to the body itself. In this way, the region omega becomes time independent, of course. And so in this case, if we denote by capital U the total velocity of the body, so translation plus the rotational velocity, we have the following equations. In the case of a passive motion, so when the motion of the body is prescribed, you see these are basically the Navier-Stokes equations modified by this term U dot grad V, because we are observing the motion from a frame attached to the body. So this comes from kind of the description, the geometry that we are considering. I'm assuming adherence boundary conditions. So the velocity of the fluid, of the liquid, coincides with the velocity of the body. And the liquid is quiescent at infinity. So the velocity must be zero at infinity. In the active case, the equations, these three equations are exact. I mean, these equations here are exactly the same, but now we have to add the equations describing the motion of the body, basically Newton's law. And so this is the equation for the center of mass. We are assuming that there is a force possibly acting on the body. And this is the equation of the angular momentum. So we are assuming that possibly there is a torque acting on the body. MC is referred to the center of mass. Now, this Q is the matrix that the one parameter family of matrices that connects the body, the frame attached to the body to an inertial frame. So it's basically the family of proper orthogonal transformations that are related to the angular velocity by a first-order differential equation, this one here, where A is a matrix whose entries is a skew-symmetric matrix whose entries are the components of the angular velocity. So when we have an active body, in addition to the Navier-Stokes equations or modified Navier-Stokes equations, we have to solve for psi, for omega, and also for this matrix Q. Okay, so now, but why did I pick these three problems out of many? they are very simply formulated. So there is no, it's really, the problems are formulated in a very straightforward way. They have been open for a long time, and also because some of them may have a bearing on other fundamental questions related to the mathematical theory of Navier-Stokes equations. So I will start with the first problem. The first problem is a simply stated Liouville type problem. Okay, so in this case, there is no body. The body is an empty set. Omega is the whole space. V depends only, the velocity and pressure, the fields of the Navier-Stokes equations depend only on x. Okay, so they don't depend on time, and U is identically zero. So in this case, the equations, the previous equations become the following. So just the steady state Navier-Stokes equations in the whole space with zero velocity at infinity. Okay, so now I will assume that V and P is a smooth solution. For this is enough that V is locally in L3, which implies right away that VP is of class infinity. And moreover, since V has to vanish at infinity, this implies that V also is L infinity, so it's uniformly bounded in the whole space. Since I will briefly touch also the n-dimensional case of this problem, I want to remind you that when n is not 3, you can have very regular solutions in the case n greater than 3, if instead of L3 you assume Ln log. And if you are in 2 dimension, this is another interesting open question. So the Ln, which would be L2 log, is not sufficient, apparently. So you have to add an epsilon here. Bringing this epsilon to 0 is an open question. So for regularity, it's enough to have Ln log if n is not 3, but if n is equal to 2, you need the L2 plus epsilon log. Okay, in any case, I'm assuming a smooth solution to this problem here. Now, in the first edition of my book, I posed the following question. So what is the minimal request on the behavior at large x, so far from the, for x going to infinity, of a smooth solution to assure that this weak solution, this solution is trivial. Okay, so now the natural class of behavior, so concerning the asymptotic behavior, is the Leray class where you prove existence. So the gradient of V in L2. Okay, so this seems to be the natural class where to prove this Liouville theorem. And with this in mind, again in the same edition of the same book, I proved the following. So if you have a smooth solution that is in L3n over n minus 1. So this is in our n in general. When n is greater than or equal to 3, then V is identically equal to 0 and grad P is identically equal to 0. So it's enough that if a smooth solution is in this space here, for n greater than or equal to 3 is automatically trivial. Now, by the Sobolev inequality, in the case n equals 3, I mean, in the general case, if the gradient B is in L2, then by Sobolev, it must be in this space here, L2n over n minus 2, if n is greater than or equal to 3. And now, the interesting thing is the following, is that since B is in L infinity, because as I said, it's regular by assumption and tends to 0 at infinity, L infinity intersected with the L to n minus 2, so whatever comes from the Sobolev embedding, is embedded in L3n over n minus 1, so satisfies the assumption of the theorem. So in other words, if you are with n greater than or equal to 4, excuse me, and the gradient of B is in L2, necessarily the assumption of the theorem are satisfied, and therefore the solution is trivial. Okay, so here is the corollary. V is a smooth solution with the gradients of V in L2, then for n greater than or equal to 4, then V is trivial and grad P is trivial as well. Now, for n equals 2, there is a famous theorem that goes back to Gilbert and Weinberger that shows that if grad V is in L2, R2, so is L2 in the whole space, then V must be trivial. And so we have this, so not yet. So now, if n is equal to 3, excuse me, now the n is equal to 3 is only the only case that we have to discuss, because for n greater than or equal to 4, the solution is trivial. For n equals 2, the solution is trivial. In the array class, what happens if n is equal to 3? Now, the condition requested by the theorem, this one here, becomes V in L9 halves. And by Sobolev, of course, we know that if the gradient of V is in L2, V is in L6. However, L infinity intersected with L6 is not contained in L9 halves. And therefore, in the case n equals 3, the theorem that I showed a moment ago does not ensure that the solution is trivial. So we know how to solve the problem for n equals greater than or equal to 4, for n equals 2. But the case n equals 3 is the only one that is left open. Now, it could be just a kind of curiosity, but this has some impact on a broader problem, as I will show you. So first of all, let's talk about this this L9 halves that comes from my theorem. Basically, in the case n equals 3, under this assumption, you have triviality. I mean, the solution is trivial. So let's discuss this. In 2003, Plechach and Schwerak considered an equation number 2, that says the same scaling and the same energy estimates as Navier-Stokes. So formally, if you multiply by W, integrate by parts, you get the same estimate that you would get from the Navier-Stokes equations. And they showed that this equation has a non-zero solution, let's call it the W bar, that behaves at infinity, smooth, it's super smooth, and behaves at infinity like x to the negative 2/3. Now, since this W bar behaves like x to the negative 2/3, you immediately find that it is in L9 halves plus epsilon, but does not belong to L9 halves. So this 9 halves seems to be a kind of, I mean, suggested by this example of Plechach and Schwerak, seems to be a kind of borderline case. However, the property that the model equation in 2 does not have is, so it's not like Navier-Stokes equation, is that it does not admit the maximum, a one-sided maximum principle that instead is satisfied by this function psi for the Navier-Stokes equation, the one-sided maximum principle. And now, the interesting thing that since 2014, if you go on math science, there are over 50 papers dedicated to this Liouville problem in R3. I don't know why there was this kind of escalation. So for basically, it was silent for kind of 20 years. And then all of a sudden, people dedicated, started thinking of this problem, this Liouville problem. And so the first was Dongo Chai, our friend Dongo Chai, and who used exactly this property that is missing for the model problem, for the model equation number 2, so that this function psi satisfies a one-sided maximum principle. And this showed that if the Laplacian of B is in L6/5, which implies that, in particular, the gradient of B is in L2, again by Sobolev, then the solution is trivial. Okay. The same problem was taken by another friend of ours, Grisha Seriegin, who proved that if V is in this BMO -1 R3, which basically says that V can be written as a divergence of a symmetric tensor, then, and also is in L6, then V is trivial as well. So basically, these two set of papers, they are studying the problem, let's say in the Leray class, not directly in the Leray class, but somehow in spaces that are related to the Leray class. Now, in this other set of papers, they studied the possible improvement of the L9 halves. And so Chai and Wolf, Jorge Wolf, they proved that, it's not L9 halves. We can relax it to by multiplying by a suitable logarithmic factor. Seriagin and Wang showed almost, that's why there is this, almost, not really, but almost, that L9 halves can be weakened to L9 half infinity, so the weak L9 half. And more recently, Harren proved that you can still, the 9 halves can be somehow generalized to weak spaces of the form L9 halves R, where R is in Lorentz spaces, where R is greater than or equal to 9 halves, but infinity excluded. And more recently, these results of Chamorro, Harren, and Lemarie-Jusset, where V should be, could be in LQ, where Q is between 3 and 9 halves. Now, this seems to be kind of redundant given my result. But however, they do not assume that V is in L infinity R3. So it's a kind of generalization of my result in the class of non-regular solution. Without assuming, not non-regular solution, but without assuming any condition at infinity, because the solution is regular. Okay, so now, why this problem may have an impact on the initial problem. Okay, so let me explain this point. So the existence of a non-trivial solution can have an important impact on the regularity problem for the initial value, the regularity question for the initial value problem. So now we're considering the initial value problem here. And as you know, in 1934, Leray showed that if we have a mild solution to 3, this mild solution can develop a singularity at a certain time, capital T, if develops a singularity, then the rate of blow up should be this one here. Okay, should blow up like capital T minus T to the negative 1/2. Now, let me define, recall the definition of an ancient solution. So an ancient solution is a mild solution that is defined in minus infinity capital T times R3. So steady state solution is a particular case of an ancient solution, of course, because it exists for all times. So steady state solution is a particular case. Now there is this interesting result of Koch, Nadirashvili, Seriagin, and Shverak that says that if we have a finite time singularity, so if you have an ancient solution with, if we have, a mild solution that develops a time singularity, then this solution must generate a non-identically zero bounded ancient solution. So if we have a singularity, necessarily starting from this solution that has a singularity, we can generate another solution that is ancient and bounded. So is in L infinity minus infinity times R3. And so the existence of a non-trivial steady state solution in L infinity R3 would provide the existence of a non-trivial bounded ancient solution. So the existence of such a solution could put some serious questions on the regularity of a mild solution. So that's why I think that this problem is, besides the interest per se could be could shed some light on a much more interesting problem. Not a much more interesting, but a much more debated problem. Now, a final remark concerning this question here is the following: is that if we assume that the velocity at infinity is non-zero, okay, so we consider this problem plus this condition here on the velocity, so that v tends to a vector that is a generic region motion, then one shows that v must be trivial. So v must coincide, of course, in the Leray class. If we're in the Leray class, then v must be trivial, must be the rigid motion. And this was showed by Babienko when omega is not zero, and by Matsky and myself when omega is non-zero. So this problem basically is really open just when u is equal to 0 and n is equal to 3. My gut feeling is that there is a non-trivial solution. There is a non-trivial solution, but of course, finding it, it's another thing. I mean, just another side, interesting open question when u is not 0. So we are in this case here, is to show, this is another interesting question, is if you have a Liouville theorem, but only in the class of functions that are essentially bounded. Okay, so this is my first problem. My second problem concerns what is called the free fall problem. So let me describe what this problem is. So now this body B is subject to a given force and no torque. So I am eliminating the torque. So there is just a force that is acting on the body. And we want to find the motion of this body. So B is active. So the motion of B is part of the problem. And so we have the modified Navier-Stokes equations. We have zero torque here, and we have the force, and of course an equation for the family of orthogonal transformations Q, given by this. So now the question is to prove existence of a global strong solutions for small data. Okay, so we don't care about the size of the data, just small data. And there is a long list of results. Now, a long list of the results provided F satisfies this important condition here. So F has to be in LQ in time. Of course, by the way, this F here is only a function of time because F is the force acting on the body. So on the body, and we assume that it's only a function of time. Okay, so F is LQ in 0 infinity for suitable Q. Then under these assumptions, the question has a kind of not trivial but straightforward positive answer. And this can be obtained can obtain either directly or as a consequence of these works here. Ishida was the first to study this kind of problems, then Anna Silvestre and myself, then Heber and his associates, then again Shibata and Ishida and others. 1 second, I have a question in a chat. Yes, I will come in a second what the strong solution is. In fact, I think I say it later on, but well, if I don't say it later on, I say it now. So for me, strong solution is a solution that I think I give the definition, but it's a solution. Oops, is a solution that basically, so B is a solution that is such that B minus U, because we are in an exterior domain, is L infinity 0 0 infinity L2. So it's a Leray intersected with the L2 0T W12, okay? And moreover, has, you know, the second derivative of V in L2 0T L2. The first time derivative is in L2 0T L2. Okay, so this is a strong solution. Strong solution in the sense of Prodi, in the sense of Prodi-Ladizenskaya, basically. Okay, and also so that I have, I can write these equations almost everywhere, basically the original equation almost everywhere. Okay, all right. So there is a bunch of papers dedicated to this problem, but again under the assumption that F is in LQ0 infinity for some Q. Okay, and we will see why this is important. And here is the importance. So there is a fundamental tool that is the energy balance. So formally, you multiply your equations by, you multiply this equation by V, integrate by parts, use these two equations here, one for the center of mass and the other, for the velocity of the center of mass, and the other for the angular momentum, and you end up with this energy balance. So basically it says that the kinetic energy, this is the total kinetic energy, plus the dissipation in the time interval 0t, must be equal to the work done in the interval 0t by the force F, plus the initial data. Okay, so now if F is in L1 0 infinity, then you can increase the right-hand side as follows, right? Plus the initial data. And from here, you can easily obtain a uniform bound. So that basically tells you that V is uniformly bounded in L2, and so is the translation and angular velocity. And so the total dissipation, everything is bounded in terms of the initial data. So it's crucial that F is in L1 0 infinity to get this kind of uniform bound. Once you get this uniform bound, then you can play around by more or less, classical procedure, and you can show the existence of a global strong solution, strong in the sense of the definition that I gave a moment ago, for small data. And in addition, this solution tends to the rest, you see, because the velocity tends to 0, the angular velocity tends to 0, and the V tends to 0, at least in these norms, okay? So now, I would like to point out, this is important, that in the L1 sense, Ft, the force, tends to 0. And the corresponding solution tends to 0 to the rest, which is the only steady state corresponding to F0. So the force tends to 0, and the solution to the time-dependent problem tends to the only steady state solution corresponding to the 0 force, which is the rest, okay? So now the free fall problem, I take a rock and I drop it in a liquid under the action of gravity. So now the force acting on the body is gravity. And so the equations become here with the, they can be simplified. You see that there is no longer the Q matrix equation. It has been replaced by this equation on the direction of gravity. Because of course, even though the direction of gravity is known in a fixed frame, from a frame attached to the body, the direction of gravity is an unknown. And here is the equation that the gravity has to satisfy. So there is no longer, the matrix Q is no longer there, but is replaced by an equation that describes the variation of the direction of gravity with respect to the frame attached to the body. So here, the only driving mechanism is what is called the effective mass. So the difference between the density of the body and the density of the liquid. And we will assume that this is positive, which means that the body can really fall. If it was negative, the body would go up. It's a question of buoyancy. Here, the buoyancy is negative. So the difference is positive. Anyway, so this is the driving mechanism. So this is the quantity that if you want strong solutions, you may assume to be small. This the equation for the direction of gravity tells us another important thing, that of course, as expected, the magnitude of the gravity is constant. Of course, it's 9.8 meters per second squared. And the third thing is that I'm assuming just zero initial data. So I'm dropping this body from rest. So the simplest situation possible. I take this body and drop it in water, in a Navier-Stokes liquid. Now let's go back to the energy balance. So the energy balance, again, you have the kinetic energy dissipation, and now this is the work done by the gravity on the body. I see there is this effective mass in front of it. So if the effective mass is zero, so if the density of the body is equal to the density of the liquid, everything, basically there is no motion, everything is equal to zero, so nothing moves. So this is the effective mass that is the driving mechanism. Now, in this case, and unlike the previous case of a generic F, we have that the magnitude of gravity is constant. So the only thing that we can obtain from this energy balance is this inequality here, and we lose the uniform bound. So the only thing that we can say from the energy equation, from the energy balance, is that the kinetic energy plus the dissipation is bounded by an increasing function of time, is an increasing function of time. And so this is not enough to prove, at least by the methods that are known, it's not enough to show the existence of a strong solution, even locally. But, sorry, not locally, but a global strong solution. In fact, if we use this non-uniform bound, nevertheless, we can prove a local strong solution for arbitrary effective masses. So we show the existence of a local strong solution. But the question is if we can prove a global strong solution for small effective masses. So basically, if we can prove that this body can really, dynamically speaking, can fall, for a long time, for all the time it wants, at least for small effective masses. Okay, so this, we don't know. We know locally that the body can fall for a small time, but we don't know if the body can really keep falling for all times, at least for small effective masses. So now, what is the conceptual difference between a generic force that satisfies these asymptotic properties and gravity? Okay, so in case F, for generic forces, for forces that are summable in time, this Ft tends, of course, in the sense of L1 to 0. Here, the gravity is constant. The magnitude of gravity is constant at all times. So in case A, there is one and only one steady state solution corresponding to F naught equals 0. However, in the case of the free fall problem, the set of steady states could be very rich, even at arbitrary small effective masses. So in other words, while in case A, the flow knows where to go, roughly speaking, for small forces, it goes to rest, because rest is the only steady state. In the case of this free fall problem, there could be more than one steady state, and to which one of these, for small effective masses, is the flow going? So what is the terminal state that the flow has to reach? Okay. Now, Denisler in 1987 showed that for any given effective mass, there exists at least one steady state solution. And in fact, his construction, the existence construction, that is based on a finite dimensional approximation, the Colloquium approximation, existence for the finite dimensional approximation is proved by a degree argument of a suitable map. And the degree of this map is equal to 2, actually. And this suggests the existence of multiple solutions. So there is more than one. Even the abstract proof followed by, used by Denis Serre, implies, or at least suggests, the existence of more than one solution because the degree of this finite dimensional map is even. Now, you can really show that, in fact, there are a bunch of steady states. So the steady state problem has definitely known unique solutions. In particular, consider, let's define a body symmetric under a direction, around a direction A that I take coinciding with the E1 axis. If it happens that if I change x2 into negative x2 or x3 into negative x3, I still go from one side of the body to the other side. So basically, if I change x2 in negative x2 and x3 in negative x3, I still am on the surface of the body. And so for these symmetric bodies, in many years ago, I proved with Ashwin Vaidya the following theorem. So suppose that I have a body with a positive effective mass. And this body assumes that it's Lipschitz and symmetric around the k greater than 1 distinct directions, okay? Then there exists at least k distinct steady state solutions with omega equals 0. So they're only translating. So the body in this steady state solution is only translating. There is no rotation. And this translation velocity is parallel to g and parallel to the directions of symmetry, these distinct directions. And these directions, they correspond, these steady state solutions corresponding to as many orientations of B. So without, forget about this theorem, I give you a typical, a picture of a pictorial representation of the theorem. So assume that you have a cylinder, okay? So this cylinder has two axes of, two principal axis is symmetric, let's say, according to the definition, about two directions. A direction that is just the axial direction, and in fact, any direction that is orthogonal to the axial, to the axis direction. Okay, so these are two possible. These two folds are possible generates possible steady state, not possible, generates steady states. In the case of a parallelepiped, you have three possible steady state solutions corresponding to the body falling along axes that are orthogonal to the three different faces, sides. In the case of a cube, we have 13 steady states that are obtained by the gravity being parallel to either two axes that are orthogonal to faces, or they go from side to side, or from vertex to vertex. So there are three of the first, three possibilities in the first case, 4 in the second case, and 6 in the third case. So you see here you have 13 steady state solutions. Here you have 3 steady state solutions, and here you have 2 steady state solutions. So we have to decide, and we have to understand towards which of these steady states we want to construct strong solutions. We have to understand toward which one of the steady state solutions the body will go. Now, it is reasonable, of course, to guess that for small, especially for small data, the coupled system liquid body will reach the steady state for which, the steady state configuration where B is in a stable orientation, okay? So it is reasonable to, to predict or to guess that the flow, the coupled system will go towards that steady state that makes B stable, whose configuration will make B stable. And so now, in the simplest case, when you have only two, possible orientations of the body, now experiments shows that this one here, the one that is orthogonal with the axis orthogonal to gravity, is the stable one, And this one here is unstable. Okay, so an idea, but you know, the implementation of the idea could be complicated, but the idea is just to you know, to construct possible strong solutions is the following. So we take the steady state that corresponding to the stable solution, okay? And then we perturb this steady state by these quantities, okay? And prove that this perturbation to the stable steady state is strong and global for provided, of course, the effective mass is sufficiently small. So the idea is to construct a strong solution around the stable solution, which in the case of a cylinder, experiment shows is this one here. So with the long axis that is orthogonal to the gravity. Now, just to make it clear, the typical difficulty that introduced in the Navier-Stokes equation to prove a global strong solution by the nonlinear term is absolutely irrelevant in this case. So in other words, you can disregard the nonlinear term in the Navier-Stokes equation, and you still don't know how to construct strong solutions. So, okay. And now, finally, the third problem, which is something that I remember I briefly discussed, really briefly discussed with Igor 11 years ago, actually in 2011, when I gave another, a seminar at USC. So it's the long time behavior of a flow past a body. So now it's the nice picture is here. So you have a flow past a tennis ball. So all problems related to turbulence, and but I don't want to go that far. My problem is this. Really it's basic. So from the mathematical point of view, the motion of B is prescribed. So B is passive in this case, and the U is directed along the E1 axis and is time independent. So U is lambda. Lambda is a parameter, positive parameter, and omega is equal to 0. So the equations are the following. If I defined by this partial 1 as the derivative of with respect to x1. So this is the problem I'm interested in. So the velocity at the boundary is this lambda E1. Velocity at infinity is equal to 0. Initial velocity is even equal to 0. I don't care. It could be non-zero, but I take the simplest case where the initial velocity is equal to 0. Okay? And so what I want to do here, I want to study the behavior in time of the solutions to this problem here. So what happens to these solutions when t goes to infinity? Okay. Okay, so now the basic difficulty in studying the behavior as t goes to infinity of the solution is due to the fact, and I want to study this, whatever this lambda is, whatever the number lambda is that I put here, small, large, I don't put any restriction on this lambda. I just want to know for given arbitrary lambda, what is the behavior in time of solutions to this problem here, okay? Now, the difficulty is just this, that lambda is time independent. So the driving mechanism is time independent. So we are basically pumping into this fluid energy at a constant rate, roughly speaking. Lambda is independent of time. Now, what can we say about the behavior at infinity of these solutions? Now, if lambda is small, there is a result that, what was that? 25, my gosh. 25 years ago, John Haywood, Yoshiro Shibata, and myself proved. And it's the following. So let's denote by Vs of lambda a steady state solution to this problem here. So basically, to the steady state problem, to the steady state form of the previous problem is a steady state solution, okay, to this problem here, to this problem here. Okay, so corresponding to the given lambda. Then there exists a lambda star positive such that for all lambda less than lambda star, the steady state solution is unique, and the time dependent solution of the previous problem tends in the L3 norm to the steady state. Okay, so the problem for lambda small is solved. For lambda small less than this lambda star, the solution to the time-dependent problem, to this problem here, tends to the unique steady state solution. The question is, what happens if lambda is large? So in other words, what is the ultimate dynamics of the flow? Can we talk about the global attractor, assuming that the solution exists for all times, and you have also possibly uniqueness properties? So this is really a higher order question. The question is really very simple. So the basic question is the following. That is, of course, at the basis of all these other questions. So given an arbitrary lambda positive, can we find a norm in which solutions remain uniformly bounded? That's the question. So given lambda arbitrary, can we find a norm in which the solution for all times is bounded only in terms of lambda, the data? Lambda is the only data. Now, it is well known that if omega is bounded in at least one direction, we may take this space to be L2. And this is equivalent to the energy being uniformly bounded. This goes back to Ladizeska in 1975, but there's a plethora of papers and books written on the topic. Now, in our case, so when omega is an exterior domain, it can be shown, and I will show it to you, that the space X, or whatever you pronounce that thing, cannot be L2. So in other words, the energy is expected to be unbounded, even for small lambda. The energy is expected to be unbounded in time. In fact, take lambda less than lambda star, where lambda star is the same lambda star of the paper with John Haywood and Yoshihiro Shibata. And suppose that the kinetic energy is bounded in L2. All right, then, since it's bounded in L2, we can find an unbounded sequence, let's call it T sub m, and some V hat corresponding to L2 that maybe depends on the sequence, such that this sequence VTM tends to V hat in the sense of distribution like that. But of course, since lambda is less than lambda star, this V hat must coincide with the steady state solution corresponding to that specific lambda, okay? So the steady state solution should be in L2. However, it's known since the work of Finn in 1965 that this VS, the steady state solution, is not in LQ. Is in LQ, sorry, in L2. Is in LQ for any Q greater than 2, but is not in L2, okay? And therefore, this cannot be true. The energy has to be unbounded. Okay, so one may thus, try to take this space, this unknown space X, to be LQ for some Q between 2 and infinity, of course, excluding 2. Of course, if we would be able to prove that B is uniformly bounded for all times in LQ for Q between 3 and infinity, that this basically would imply the existence of a global regular solution. So we will win a 1 million prize. So this is very unlikely to happen. So Q greater than or equal to 3, if we decide to pick X to be LQ, is very unlikely. However, we may try V in LQ with Q between 2 and 3. And this would be on no harm to the outstanding open problem of global regularity. So the question is, can we show that the original for the original problem, the LQ norm of V is, where Q is between 2 and 3, is uniformly bounded in time? So I don't know what the answer is, but we could start, one could try to start to study a model problem of this form. So instead, I replace the bound. First of all, this is in the whole space. That helps. So there is no boundary that could, cause problems. There is no boundary condition, therefore, so I replace the constant in time boundary condition with a force F that is depends only on space, and I assume that it's a C infinity with a zero average, for reasons that I will tell you in a moment why zero average. But the force basically is C0 infinity in space, not in time. So we are pumping energy into the system at a constant rate. And the question is, do there exist global, even weak solutions, such that, of course, weak solutions, do there exist global weak solutions such that V is in L infinity, 0 infinity, LQ for some Q between 2 and 3? So that is uniformly bounded in LQ in terms of the data. So, the first question that you may ask for this model problem is that, well, is there, of course, disregarding this initial condition, but can you find a steady state solution for this problem here? And the question is yes, if you assume a steady state solution, of course, in this class here. And the answer is yes. If you assume that the average of this force is equal to 0, you definitely have a steady state solution. So the problem makes sense. In addition, of course, you add this initial condition to make things even simpler. So that is the question. Given this equation, this is just a model problem. So given this equation here with the force that C0 infinity in space and 0 average, can we find a solution that is uniformly bounded in LQ for some Q between 2 and 3? Or alternatively, which would not be in contradiction with the steady state problem that we mentioned a moment ago, that the grad V is in L infinity capital T infinity for some sufficiently large T. This is somehow suggested by the energy balance. So, or if you wish, any other norm that for which we can find V uniformly bounded in time. And this, I guess, it's it's something that really is a basic question to answer if we want to answer more complicated questions like the ultimate dynamics of a flow past an object. And so basically conclusions. So I have discussed 3 of the many, I must say, challenging open problems for the Navier-Stokes equations past the body. And the hope is that we find someone interested mathematician, maybe junior, with that can think out of the box, who could find a way to break the deadlock and so will contribute to the solution of one of them. And my personal belief is that answering one of these questions would really open a new avenue, new understanding of aspects, or at least to unveil new aspects of the Navier-Stokes equations that are, at the moment still not completely understood, or not understood at all. Okay, and so with this, I thank you for your attention.